Okay, thank you. Thanks for the invitation. I really like these events, although it's not always very convenient for me to be present live. So this single, I modified slightly the title compared to the announcement because I would like to discuss also systems where you don't have a single spins, but the physical underlying physics is the same as for single spins. So the topic is about magnetic resonance, which you are all familiar with, I assume, since this is a NMR seminar. So we have typically some interaction like a magnetic field, some energy difference, and we measure this energy difference by applying a resonant radio frequency or microwave field. The one thing which many people are concerned with this technique is that very often the sensitivity limits the applicability. So it's generally considered to be a low sensitivity technique, but it depends, of course, with what you compare it. And one way to look at it is that you can say the nuclear magnetic moment is small. In a Tesla field, the energy of a single proton is less than 10 to the 10 to the minus 26 joule. That is much less, about 1 million times less than the detection limit, which is determined by the thermal energy at room temperature, would be 10 to the minus 20 joules. So it sounds difficult. On the other hand, of course, we have a signal that is normally not from a single nucleus, but from a very large number of nuclei. For instance, if you look at the human body, you will have several times 10 to the 26 nuclei, which give you a total magnetic moment of about 1 joule per Tesla, which should be large enough for many applications, and that's why we get very nice images of a human body. But what about small samples? And I would like to give you some examples from small samples which show where you can get with conventional inductive detection and where it becomes increasingly difficult. So this is a scanning electron microscope image from one of our smaller samples. This is a multi-wall carbon nanotube, which is filled with crystalline iron. And so this is actually not nuclear magnetic resonance, but ferromagnetic resonance or electron spin resonance. So the size of that sample is a rod-like system with about 5 nanometers in diameter, or a bit more than 5 nanometers in diameter, but a length of some micrometers. That is relatively small compared to typical NMR samples, but of course you can go smaller. Like this is a really small sample with about 42 nanometer in diameter and a thickness of about 100 nanometer. So here you have a volume which I express here in septoliters, or you could calculate the number of spins in that system, which is fairly small, but it gives you still a reasonably good signal. Still, you would like to go smaller. We talked about single spins. So how small can you really go? Now, this was measured at room temperature, and one way to go to smaller samples and keep the sensitivity is, of course, to cool the system. So if you go lower in temperature, you have two advantages. First of all, you increase the polarization, so the number of excess nuclear spins becomes larger, and at the same time, you reduce the noise. Now, this does not mean that you gain much by going to 0 degrees, as the snow here suggests, but you have to go really low, say to 4 Kelvin or even lower. If you do that, then you can significantly reduce the noise. Depending how you measure it, it goes down with temperature by maybe 2 orders of magnitude. The blue line represents the theoretical limit for noise. The data points and the red curve represent the actually measured thermal noise for a specific system. Obviously, you can increase the sensitivity, and this is the actual signal to noise in such an experiment. It increases quite dramatically if you go to low temperature. And you can actually expand that to if you go to even lower temperature and special purpose amplifiers and detectors that allows you to do single spin electron resonance with kind of inductive detection. This was demonstrated a few years ago by a group from Paris. Now, this requires some very special hardware and is not applicable to general purpose samples. So we would like to look at other options and also at techniques which are still applicable at room temperature, not just at millikelvin temperature. And this is where we come now to the optics part. So the reference that I would like to look at here is laser spectroscopy. Laser spectroscopy is a bit like magnetic resonance, except that you don't use microwave or radio frequency field, but use optical fields to measure energy differences between different electronic states normally. And this changes the characteristics compared to magnetic resonance quite drastically, in particular, if you look at the sensitivity. So experiments with single atoms, molecules, ions, and so on became possible even in the last century. Like this picture here shows the red dots, which are individual magnesium ions, which were trapped in a linear pole trap, here from a publication in 1992. So the sensitivity is definitely very high for this kind of spectroscopy. But there are some other interesting characteristics like the time resolution that you can get with lasers or the frequency resolution. In the case of optical clocks, you can reach frequency resolutions, a relative frequency resolution of 10 to the minus 18. So why should we use lasers for magnetic resonance? I already mentioned the sensitivity, which can be increased by many orders of magnitude, reaching the single spin level. And the reason for that, for this sensitivity increase, consists mostly of two parts. One is that you can increase this polarization. So in nuclear magnetic resonance at room temperature, you typically have a relative polarization on the order of 10 to the minus 5 to 10 to the minus 4. If you optically pump your system, you can bring all the spins into the same spin state, so the relative polarization is close to unity. The second reason is that you increase the signal energy that you get on your detector. In NMR, your photons, your radio frequency photons, have a signal energy on the order of 10 to the minus 25 joules. If you use optical photons instead, the signal energy increases by about 6 orders of magnitude. So that means they're much easier to detect and they don't have to compete with noise. So let's look a bit more closely again at the polarization. This is normally, if you have thermal polarization given by Boltzmann's equation, which says that the ratio of the spin up versus spin down population is given by the energy difference divided by the thermal energy. Now, if you put in numbers, say a typical Larmor frequency and room temperature, you find that this comes to the 10 to the minus 4 to 10 to the minus 5 range that I mentioned before. So the thermal energy in this case is much larger than the Zeeman energy by several orders of magnitude. And this is completely different if you go to an electronic system. So here the optical excitation would be on the order of a few electron volts, which is again orders of magnitude larger than the thermal energy. So in optical systems, you have all the population in the ground state, you have a high polarization, and what we try to do in the following slides is to transfer this polarization from the optical system to the spin system. That's a process called optical pumping. So this was about sensitivity, how to improve the polarization and increase the sensitivity. There are other reasons I will briefly touch upon. One is selectivity. You can use the laser to select specific times or chemical environments or orientations in a sample. It just gives you an additional degree of freedom, which can be useful for getting information. Excited states can be prepared with laser pulses. And so if you want to measure properties of atoms or molecules in excited states, you will need a laser anyway. And together they can give you interesting additional information. Also, in some cases, you can create the polarization much more rapidly. Typical example is diamond. If you wait for thermal polarization of nuclear spins in diamond, this can take days until you get thermal equilibration. With a laser pulse, it will typically take you some microsecond to get full polarization. So you gain a lot in terms of speed. So if we want to use that, we need, in addition to our normal magnetic resonance setup, some optic setup. So we need a laser, we need optical detectors, and together this gives us something which I like to call laser-assisted magnetic resonance. So the combination usually you have the sample here, you have a laser irradiation, you have radio frequency or microwave irradiation, and you have some optical detection. I will discuss that in a bit more detail. Now, let's start to discuss the physical principles that we use here. First, about increasing the spin polarization. As I mentioned, we would like to go from thermal polarization to ideally unit polarization. How can we do that? One possible approach is to consider that angular momentum or spin is a form of angular momentum. Now, you probably all have learned at some point that angular momentum is a conserved quantity, at least in an isotropic environment. So that presents in a way a problem. If we want to increase the polarization, we have to increase the angular momentum in the system. And since this is a conserved quantity, we cannot just increase it, but we have to transfer it from somewhere else. So let's look at possible sources of angular momentum. As I say, it's conserved in free space, and the possible reservoirs that are relevant for us are, first of all, the electronic orbital angular momentum. So That depends whether the electrons that we consider are in an s, p, d, f or so orbital. That means they have an angular momentum of 0, 1, 2, 3, and so on. That's one important source. Then we have, of course, the electron spin and the nuclear spin. These are the most important ones for magnetic resonance. They're not independent of each other. And we have, for instance, interaction between the orbital and the spin angular momentum of the electron, which is known as fine structure from atomic physics. And of course, we have the interaction between the electron and the nuclear spin, which is known as hyperfine interaction. What we have to add now is the photon spin, which is the most important additional source that we consider here. Photons have an angular momentum of h bar, so their spin quantum number is 1. Now, if you want to use the photons, they don't interact directly with the nuclear or the electron spin, but they do interact with the electronic orbital angular momentum through absorption and emission. And photons are particularly interesting because it's fairly easy to create spin polarized photons. You can have them in arbitrary amounts essentially, and they're cheap and you can manipulate them very precisely. So this is probably the ideal source if you want to polarize your spins. Now, let's look at the specific situation. Let's assume we have a laser beam with circularly polarized light. That means the photons are all polarized parallel to the direction of propagation. And let these photons now interact with an atom, which we assume to be in the ground state. It has an angular momentum of h bar over 2, polarized in the down state, as you see here. Now, if this atom absorbs the photon, that means the photon vanishes, its angular momentum is gone, but we have to preserve angular momentum. So the atom can only absorb the photon if it changes its angular momentum state. It goes over into change, again, in this situation, again a J equal 1/2 system, but the Z component is now plus. So this is a typical situation, and that's the basis of a model for optical pumping, which was developed by Alfred Gassler in 1950. So we have here two electronic states, a ground state and an excited state. Both have angular momentum of 1/2. And we irradiate this system with circularly polarized light. So if we choose the right polarization, only this specific transition can occur because that's the only one that preserves the angular momentum of the photon or of the total system during absorption of the photon. So if we absorb a photon, the atom goes up into the excited state and switches its orientation. For spontaneous emission, it can drop down to either of the two ground states. If it goes back to the original one, nothing has happened in total. But if it drops to the J equal plus 1/2 state, we have created an imbalance of the spin orientations. And you can repeat that. And if you do that often enough, you get a highly polarized spin state. That means you have increased the polarization, spin polarization of the atoms. Again, the basis for that is conservation of the total angular momentum, which works with free atoms because this is in an isotropic environment. If we switch now to a solid state system, here in this case it's gallium arsenide, obviously the environment is no longer isotropic. So angular momentum is no longer a conserved quantity. However, Depending on the symmetry, there can be some remnants of angular momentum conservation. In the case of gallium arsenide, the system has cubic symmetry, which is still relatively high symmetry. So we get some partial conservation of angular momentum. So we can still use the argument of angular momentum conservation to some degree as long as we're careful. So in what sense does that apply to gallium arsenide? The absorption occurs when you will bring an electron from the valence band to the conduction band. And for this, it matters in what type of orbitals the electrons are. In the valence band, the orbitals are p-type, so the angular momentum is 1. And in the conduction band, the orbitals are s-type, so the angular momentum is 0. That means this is an optically allowed transition. It's possible to absorb a photon with a high transition probability. Now, in both cases, the conduction band as well as the valence band, we have interaction between the orbital angular momentum and the spin angular momentum. That means in the ground state, we have a total angular momentum of 3/2 and the excited state of 1/2 if we include the spin of 1/2. So we have in this case for circularly polarized light again, two possible transitions here with actually different transition probabilities. If you do that, you will create some spin polarization in the conduction band, but you will not get unit polarization. Now, in the experiments that we normally do, we actually use not a single crystal, but we use a quasi two-dimensional system, a so-called quantum film. In this case, there is confinement in one direction, and this confinement breaks the symmetry. And the result is that two of the spin states, or the total angular momentum states, have different energies. And therefore, if you have your laser resonant with the -3/2 to -1/2 transition, it's not resonant with the -1/2 to +1/2 transition, and you only excite this specific transition. So the result is that your electrons are now fully polarized in the conduction band. So this was for gallium arsenide, which still has a relatively high symmetry. If we go to systems with even lower symmetry, like rare earth ions, where you have not only a stronger interaction with the crystal field, but you also have a larger number of electrons, you can get can completely quench the angular momentum of the electrons. So in this case, optical pumping does not work anymore, at least not in the same way. That doesn't mean that you cannot use lasers to polarize your spins. In this case, we will be looking at the nuclear spins, but there are different mechanisms that you can use. In particular, in these systems, the optical transitions are relatively narrow. They can be in the kilohertz range. At the same time, the nuclear spin has relatively strong interactions with the electric quadrupole moment, for instance, and you have large nuclear magnetic moments. So the transition frequencies between nuclear spin states can be relatively large, significantly larger than the line width of the optical transitions, at least the homogeneous optical transitions. So we can polarize the nuclear spin by choosing not the angular momentums, but by using narrow bandwidth lasers, and I'll show you in a moment how that works. This procedure is called spectral hole burning, if we look at inhomogeneously broadened states. It has a number of applications. For instance, there these systems are quite popular for storing photons, for instance, for quantum communication. And people have been able to store photons in nuclear spins for up to 15 hours. So what does spectral hole burning mean? For this, I consider here a system with an electronic ground state and electronically excited state. In the ground state, we have at least two different nuclear spin states with different energy. Now, if you apply a narrow bandwidth laser, you will excite nuclear spins or ions into the electronically excited state, and they may switch their orientation during this process, but they will not stay there forever. Again, like in the case of optical pumping, they can drop down, and if they end up in the opposite spin state, which is outside of the line width of the laser, they will no longer be excited. The result is that again, you have created an imbalance between the nuclear spin states. You have increased nuclear spin polarization. Now, as you see here, the optical line is usually inhomogeneously broadened. So it means in the ensemble, you have very many of these uh, three-level systems at somewhat different frequencies. So if you want to see this polarization, you have to actually use a test laser beam, which you scan across the line with respect to the pump laser beam. Now, if the test laser beam and the pump laser beam have the same frequency, that means the test laser beam interacts with the same transition as the pump laser, it hasn't got much population left here, so the absorption will get significantly smaller, and that's known as a spectral hole. Now you have burned away the population into a different state, but you have not eliminated those ions. So you have created a larger population in different state. And if the test laser beam interacts now with the transition from that state to the electronically excited state, you will actually get increased absorption. So this increased absorption is also known as an anti-hole. And of course, this you can have the opposite situation also, that you pump it from the higher lying state into the lower lying state. So these anti-holes usually occur symmetrically at positive and negative frequency differences. And if you measure the distance between the hole and the anti-hole, you get completely without radio frequency or microwave, just by using lasers, you get the Larmor frequency of the spin, or at least the transition frequency between the nuclear spin states. This is an imaginary three-level system, just a model system, but here is an actual spectrum from a real system. In this case, the nucleus is praseodymium-141 in yttrium aluminum oxide. You see you get a relatively complex spectrum with 7 holes and about 40 anti-holes all over the spectral range. If you analyze that, you get all the necessary parameters. Now let's switch gear again and move to a different system, the diamond. So diamonds are nice, but they're also pretty boring. If you look at diamond, just have carbon atoms in a very regular lattice, and they don't really interact much with lasers, at least not in the visible range. If you want to have something interesting, you need so-called defects. The most popular defect is the nitrogen vacancy center, which you get if you remove 2 of the carbon atoms. One of them you replace by a nitrogen, and the second one you leave empty. So you have a nitrogen atom adjacent to a vacancy, and that's called the nitrogen vacancy or NV center. And this defect is also called a color center because in opposite to diamond, it can absorb and emit light. So if you microscopic scan over a diamond, you will usually find such bright spots, which can be nitrogen vacancy centers. And you can then zoom in into one of them, and that's how you do experiments with single spins, electronic or nuclear ones. Now, in the case of diamond, you also have reduced symmetry, not isotropic, and so the angular momentum is quenched. You don't use optical pumping with circularly polarized light, but again, you can do spin polarization just by laser irradiation. The mechanism here is a bit different again. It's based on intersystem crossing, and I would like to explain briefly how that works. This is the energy level system of the NV center. The ground state is a triplet A2 state, and the excited state a triplet E state. They are separated by about 2 electron volts. What you usually use for excitation is a green laser, which has a photon energy of about 2.2 electron volts. So you absorb the photon, you get somewhere above the excited state, but it quickly drops down. And after a few nanoseconds, it goes back to the ground state. Both the excitation leads to a first approximation. So if you start up in the ms equals 0 state, you end up in the ms equals 0 state. Except when this is not the case. And then the system crosses over from these triplet states into the singlet manifold. And this is called intersystem crossing. And it happens preferentially if the electron spin is in the ms equal plus or minus 1 state. During this process, it forgets where it started, and it therefore ends up preferentially in the ms equals 0 state. So the result, if you go through that many times, is you populate the ms equals 0 state, and again you have created spin polarization. So that's a useful process, and it's essential for doing magnetic resonance in NV centers, but also in many other ones, like in silicon carbide or in molecules. I would like to show one molecule which is similar but different also. The main difference here for pentacene is that here and in most molecules, the ground state is actually a singlet state. So if you don't use a laser, there is no electron spin in the system. But if you excite it with a laser from the S0 to the S1 state, you can again have intersystem crossing, in this case to a triplet state. And this intersystem crossing can be spin selective, so you get different populations of the 3 triplet states. And these different triplet states also have different decay rates to the ground state. So the phosphorescence, similar to fluorescence, has different rates. So you get different intensities from them, and you get different populations. And by applying microwave fields, you can measure ESR from the excited state, and you can also get polarization on the nuclear spins, like a carbon-13, for instance, and measure NMR transitions. In most cases, when you use optics for polarization, you will polarize the electron spin, but in some cases, you would like to have the polarization on nuclear spins. So to transfer the polarization from the electron to the nucleus requires some kind of interaction. And I start here with the example of gallium arsenide again. I showed that you can create polarized electron spins. Now, these electron spins are not point particles. They are typically in the form of an exciton, which has a radius of maybe 10 nanometers or so. So within this exciton radius, you have 10 to the 4 to 10 to the 5 nuclear spins, which interact by hyperfine interaction. And this hyperfine interaction allows to transfer the polarization from the electron to the nuclei. The problem that you have here is that you have many nuclear spins which need to be polarized to get a decent signal. And in each excitation process, the electron can only polarize one nucleus at most. So if you want to get high nuclear spin polarization, you have to repeat that many, many times. So this is a relatively slow process. You can speed it up a lot if you have a system where the hyperfine coupling is resolved. In gallium arsenide, it's not resolved. You have hyperfine interactions which are small compared to the line width. In the case of the NV center, you have resolved hyperfine interactions like you see here. You have a single electron spin, which in this case is coupled to one nitrogen 14 and three carbon 13 nuclear spins. So you get a pretty rich spectrum, and by selectively irradiating one of or a few of these transitions, you can transfer the polarization much more efficiently. So I consider here a simple situation where we take the electron spin just as a two-level system, which is coupled to a single spin one-half system. If we use a laser to polarize the electron, this is non-selective with respect to the nuclear spin. So we bring the electron spin into the ground state, the zero state, but the nuclear spin remains unpolarized. The spin up and the spin down state have the same population. So if we want to polarize the nuclear spin, one way to do that is to apply a microwave pulse on one of these EPR transitions. And now we have both NMR transitions polarized, but in opposite directions. So if we want to get full polarization of the nuclear spin, we can apply, for instance, a pi pulse also on one of the NMR transitions. So now the electron spin is depolarized, but the nuclear spin is fully polarized. So we have transferred the polarization to the nuclear spin. Now this was about increasing the polarization. What about detection? Normally, our reference is inductive detection. So we detect a photon in the radio frequency or microwave range, for instance, with an NMR coil. This is the easiest way probably to do magnetic resonance. It's very widely applicable. All the commercial NMR systems, ESR, NQR, MRI systems have this type of detection, and you can put almost any sample into such a machine. One big advantage also is that the back action on the spins is relatively small. If you do it properly, the system remains virtually undisturbed by the measurement. But as we started out initially, the sensitivity is relatively low. And this is particularly a problem when you go to low fields, say smaller or equal to the Earth field. Then the frequency becomes very low and the sensitivity very, very low. So how can we do that optically? First of all, why would we want to do that? I already mentioned that photons are easy to detect, and there is additional information that you can get from double resonance experiments. How do you do that? Well, basically, you need a measurement which depends on the spin state. There are some additional considerations. If you want to do that, you have to look at the sample that you have. Not all techniques are applicable for all samples. There are environmental requirements. What temperature can the sample be, for instance? Uh, Instrumental, what type of lasers do you need, and so on. What are the sensitivity that you can get? And obviously, I cannot discuss all these issues. Instead, I just focus here on the how. How can we do such a measurement? Let's start again with angular momentum conservation. If you have an excited state of an atom, this will emit the photon eventually, go back to the ground state, and because of angular momentum conservation in free space, the polarization of that photon depends on the angular momentum state of the initial and the final atomic state. So if you measure this polarization, you can infer the original state of the atom. This has some advantages. It has no background and it has no back action. I mean, the atom emits the photon anyway, and whether you measure it or not, it will not affect the atom. You can apply that not only to atoms, but also to some solid-state systems like gallium arsenide. If we have a spin-polarized electron here in the conduction band, it can drop down into the valence band, and depending on the states that are involved, you create a circularly polarized photon. And if you measure the circular polarization of the photon, you can again infer the spin that the electron had originally. Now, both magnetic fields and nuclear spins will affect this polarization, and this can be used also to measure, for instance, nuclear spin magnetic resonance, NMR. It's a bit different again if you go to NV centers. As we mentioned here, you don't have angular momentum conservation, but you get another property, which is the intensity of the fluorescence or the fluorescence count rate. Why is that? As I mentioned, the absorption emission process does not change the spin of the system in first order. However, uh, if and that means if you start initially in the ms equals 0 state, you stay in the ms equals 0 state and just go up and down, so you have many fluorescence photons. If you start in the ms equal plus or minus 1 state, then this intersystem crossing comes in again. The system drops down indirectly, and because during this process, intersystem crossing, there are no photons emitted and it takes time. So the fluorescence count is lower if you start in the ms equal plus and minus 1 state. So this measures the population of different spin states, and you can use that for detecting electron spin resonance. For instance, in CW experiment, you apply a laser to continuously prepare the electron in the ms equals 0 state, and then you can scan a microwave frequency across the relevant range. And if it hits the transition between the 0 and the plus minus 1 state, so the zero field splitting, then you see a drop in the photoluminescence rate, indicating that you transfer some of the population into the darker states. So this is a way to do zero field ESR. You can also apply a magnetic field. Of course, that lifts the degeneracy. In this case, you have now two transitions which are split by twice the Larmor frequency. You cannot do that only in CW mode. You can also do that in time-resolved way. If you apply a laser pulse, you prepare the system in the ms equals 0 state. So again, you have a high fluorescence rate. If you now apply a microwave pulse, you say a pi over 2 pulse, you create coherence. Now we would like to measure the coherence, but the system will not create a signal from the coherence. So if you want to do a time-resolved experiment, you have to convert the coherence back into population. That is sometimes referred to as Ramsey interferometry because it was introduced by Norman Ramsey in the context of atomic spectroscopy. If you do that, you can detect now, again, the population of the spin states. And if you change the delay between the 2 pi over 2 pulses, you get, again, something like a free induction decay, which is also known as a Ramsey fringe. Now, from the time domain signal, of course, you can get the the electron spin spectrum in this case. And for this specific example, you see that you get 6 resonance lines, which are due to the hyperfine interaction between the electron, the N14, and the carbon-13. You can use the same thing to detect NMR transitions. Again, you create population for or polarization of the NMR transitions, and then you do a Ramsey experiment on the NMR transition, and you get the free induction decay. Now, I should probably skip a few slides. I would like to just briefly describe one more experimental technique. As I said, the reference is inductive detection, where you can measure coherence. The problem is that if you use a coil for that, your sensitivity tends to be low. Now, there is a technique which also can detect coherence, but it doesn't use a coil, but it uses optical detection again. So how you do that, basically you add the microwave photon to a laser photon, you get another optical photon which is shifted by plus or minus the radio frequency. In the experiment, you need a system which has here a nuclear spin transition or electron spin transition. You apply a radio frequency or a microwave field to induce coherence between these two states. Now you apply a laser field, and that creates two coherences in the two optical transitions. And the transmitted laser beam contains now two frequencies. If you interfere these frequencies on a photodetector, you get back the radio frequency that you started out with. This is called coherent Raman spectroscopy, and it measures coherence. It has a number of interesting properties. For instance, you cannot use it only in CW, but also in pulsed mode, and you cannot use it only in the ground state, but also in electronically excited state. And I have here an example where we compare for a specific nuclear spin the transition frequency of the spin in the ground state with the corresponding transition in the electronically excited state. So the vertical axis is the NMR transition frequency in the excited state, the horizontal axis in the ground state. And you can do that for the nuclear spin, as in this case for praseodymium, or you can do it for electronic spin, like in this case, a metalloprotein named azarin. So let me skip again a few slides, and I should come to the conclusion. So What I tried to show you that photons and lasers can dramatically increase the sensitivity and the information content of magnetic resonance. There are various mechanisms that you can use to increase the spin polarization and the detection sensitivity. And you have applications in many fields. There are more, which I had to skip, but you probably, I hope you will believe me that anyway. Thanks for your attention.
All right, thank you, Professor Dieter Suter, for this very cool tutorial. It really helped me to think through the systems, even though we're doing it every day in my lab. So really appreciate it for the nice talk. Before we into the Q&A session, which are already a few questions there, I just want to take a moment to remind everyone in the audiences, if you may, use the link in the chat to complete the survey, which will be used by our Global NMR for a special event at ENC. So basically, we want to survey the community about your opinion of AI. Is that really a tool for us, a teammate, or simply a trap for magnetic resonance community? We would really appreciate that. Again, you can find the link to the survey in the chat, which is completely anonymous. Um, cool. Now let's go through some of the questions. Jeff Reimer asked, in your survey of pumping schemes, I don't think you mentioned electron spin injection from a ferromagnet into an insulator. Has this field of inquiry lost favor, or is there a new literature that has escaped the NMR community? Would you comment on that?
That's an interesting point. I'm aware that this has been tried and there is certainly some success. I'm not sure about, I haven't seen any of that in the last probably 10 years or so. Uh, I'm sure it's still being done in the context of, say, spintronics, but I'm not aware of it being used in the context of magnetic resonance.
Okay, we have another question from a anonymous attendee. Many experiments claiming single spin detection have to do signal averaging by repeating the experiment to get better signal to noise ratio. In what way are multiple experiments then different from simply having a ensemble of spins?
Uh, it depends. First of all, if you have a single spin, it means you don't have an inhomogeneous environment. So in an ensemble, typically not all the atoms or spins have exactly the same environment. Like in these rare earth ions, you have very different optical transition frequencies as well as nuclear spin transition frequencies. Uh, it's true that in most cases, like in a typical NV experiment, we do many averages, uh, but in many cases, it's also possible to do really single shot readout. Single shot meaning you initialize the system once and you don't reinitialize it until you have obtained your measurement. Still, you will typically have to acquire, say, many photons. So you initialize the spin, then you let it precess, and you monitor it by scattering many photons of the system. In systems with trapped atoms or ions, it's in a way similar. You normally scatter many photons, but in suitable systems, you can keep the state of the atom or ion unperturbed. So you can also call that a single shot experiment. what you call a single shot experiment or not, I guess, is to uh, some degree a matter of definition.
Cool. And we have another question from Macon Levitt. I've asked you the same thing long ago, but I don't think I remember the answer. Why is the photon state with n equals 0 not observed? And Macon has very thoughtfully put a parenthesis, maximum 2 minutes answers, please.
I promise. It's not correct that you cannot observe it, but in free space, and that's a result of relativity. Basically, that corresponds to longitudinal polarization, and that would, while, yeah. So because of special relativity, you can only observe two of the spin states. But for details, I guess I would need more than 2 minutes.
Well,
And sorry, in anisotropic environments, like in a solid, you can have more than two spin states. But again, it's a bit more complicated there.
cool. We have another question from Wim Wemelin. Can quantum sensing be used to study structures of molecules in the same means like classical NMR or conventional NMR?
Also, this should be in same means. Okay. Yes. I mean, it depends a bit what you mean with quantum sensing. There are some experiments where people work with single molecules. Uh, Pentosine is the most famous example. Of course, there the structure is pretty boring. There are some attempts to work also with proteins, for instance, but the amount of information that you can extract from single centers is still fairly limited. And the full structure of a protein will be very difficult to extract from such an experiment.
Yeah, I agree. If I may also add a side comment on this, I think, ultimately to use quantum sensing or let's say NV-based NMR to extract the structural information of the molecules in the same mentality as conventional NMR, we would need to resolve really the fine resonance signatures from the molecule themselves, which becomes quite difficult. Yeah, we need a high magnetic field to be able to resolve those resonances, and then we need
That
very
chemical shift
finite
information, you
filters,
mean?
chemical shift
Mm,
informations.
yeah.
And
Mm,
so, yeah, I think theoretically, yes, practically, maybe need some time. Anyways,
yeah.
that's just some my personal thought. Um, I do not see more questions. We can stay here for maybe 1 or 2 more minutes to wait to see if we have more questions. There is indeed one more question from a anonymous attendee. In some of the polarization schemes you presented, a third level is involved. Does this level accelerate the polarization relaxation rate?
I'm not exactly. So you mean, for instance, the hole burning? If that refers to the hole burning case, it just means the third level is there to pick up the population that remove from the first level. Not sure exactly what else that could, or maybe in the case of the NV center, it's just because it's a spin one system.
I think maybe the question was more referring to the NV system with the
Okay,
acute
yeah.
to it. Yeah, therefore there's a plus minus one kind of a double quantum process going on between the plus minus one states. Um, Again,
Mm.
yeah, if
But it
the
does not accelerate the polarization relaxation rate.
right. Yeah, for the person who asked this question, if you want to have a follow-up in the chat, I'd be really appreciated. And Malcolm Levitt asked, what is the main obstacle to performing these type of experiments in very high field? I don't know, that's a question for me or for Dieter. Maybe Dieter, you.
Well, there are a number of issues. One is if you want to have, I mean, say 10 Tesla, of course, even the magnetic field system for optical cryostats is not so easy to get. And if you have, say, 10 Tesla, it means that the microwave frequency would become 280 gigahertz, and the electronics for that are not so easy to get. In addition, if you say the polarization that I mentioned, that you put your system into the MS equals zero state, that is true near zero field. But the 10 Tesla, the polarization, or I mean the populations become more complex, depends of course also on the orientation of this 10 Tesla field.